Okay, let me go ahead and start taking attendance. Sixth period. Christina, yay. Audrey, yay. Baron. Okay, we're missing Patrick. Sophia's here, Kirk's here, Vaughn's here, Will's here, Charlotte's here. Jack Schaefer, Jack Shepard, Tyler, Ava, Harrison. Okay, so we are just missing Patrick. So we're going to be working on C7 notes today. So we're going to be working with linear programming. We kind of had a little bit of foreshadowing in our last lesson when we were talking about solving systems of linear inequalities. So we were graphing each linear inequality on the Cartesian plane, and we were looking at where the solution sets for each of those, the intersection, and then we kind of were describing a feasible region. So let me go ahead and share my screen so we can talk about excuse me. Okay, linear programming. Slowly but surely it should be coming up. Linear programming. All right, linear programming is very popular when you're working in industry. All industries collect some sort of data, and they have a pain point where they're trying to maximize profit or minimize costs or do some type of optimization problem. So linear programming is a method of finding a minimum or a maximum value of a function given some other limitations, some other factors, some other constraints. So the equation describing what we're trying to maximize or minimize is called the objective function. The objective function. So you may be given the objective function, or you may be asked to come up with an objective function. The limiting factors, the restrictions, are called constraints. So yesterday we talked a little bit about non-negativity constraints, when variables have to be 0 or positive. Now, those constraints, once we look at those linear inequalities, those constraints are going to confine our solution set, our possible solutions, into that shaded region of intersections called a feasible region. So how am I going to go about solving a linear programming problem? The first step is going to be to graph the system of inequalities representing the constraints. Shade what we are shading. Then we are going to, that's going to give us our feasible region. From the feasible region, we are going to identify the vertices of that feasible region, those little corners, the intersection points of those inequalities, the graph of those inequalities, boundary lines. We're going to identify the vertices, and then we're going to find the value of the objective function at each vertex. And then we're either going to look for the maximum, so the largest value of the function, or the minimum, the smallest value of the function. So it's not a difficult process. There's just a lot of steps to it. So let's go ahead and look at an example of a linear programming problem. Here you're being asked to find the minimum value as well as the maximum value of the objective function. So here's your objective function, a nice linear function of x and y, subject to the following constraints. So here is the system of inequalities that are your inequality constraints. We noticed we have a non-negativity constraint, inequality. We have another constraint where all our y values have to be greater than or equal to 1.5. We have two other constraints that we're going to want to go ahead and convert to slope-intercept form if we want to graph them. And then we're going to look at the shaded regions. So let's go ahead and graph each of these. Now, if we're graphing them by hand, we'll do it by hand, and then we'll go ahead and look at how to do it on Desmos as well, like we did yesterday. So if I'm looking at the first non-negativity constraint, the first constraint is non-negativity constraint. It's saying that all x values have to be greater than or equal to 0. So can somebody tell me what the boundary line is? What is the boundary line?
0.
I'm sorry?
0.
It's x equals 0. That is your boundary line. And what type of line is that? X equals 0.
A vertical line?
It is a vertical line. So here I have my solid boundary line, and it's saying that x has to be any number that is greater than or equal to 0. So my first constraint is going to give me this. Now remember, we can shade or we can write the arrows. It doesn't matter. The second constraint is y is greater than or equal to 1.5. What does the graph of that boundary line look like? Anybody?
Horizontal.
Horizontal line at y equal 1.5, and it's going to be solid because it's or equal to. And then if it's greater than, which direction am I shading?
Up.
Up.
Very good. Okay, so right now, if I'm looking at this, I'm already confined to this little region here, right? I'm already confined to that. That's the only part that's going to be double shaded at this point. Now, let's go ahead and look at the next one. The next constraint, oops, excuse me, is going to be this. So we can put it in slope-intercept form and graph it that way, or we can just identify the intercepts and then plot those 2 points and connect the 2 points to get the boundary line. I don't care which way you do it. Let's just for kicks go ahead and do it in terms of the intercepts. So if I'm looking for the x-intercept, that's when y equals 0. If I set y equal to 0, what is x going to be? 20 divided by 2.5, right? What is 20 divided by 2.5?
8.
8. Okay, so I have an intercept. I have my x-intercept, 8, 0. Now, what is the corresponding y-intercept? When x is equal to 0, what? 4. Very good. So I have another point, 0, 4. If I were to connect those 2 points, I'm going to get this solid boundary line because it's or equal to, and am I going to shade above or below? Look at the inequality, less than or equal to. Am I shading above to the right or below and to the left?
Below to the left.
You are correct, below and to the left. So now I'm even confined to that little triangle. Okay, but we have another one. So let's get the other one going. Let's look at this one. Let's again do it with the intercepts. I kind of like it. So if I'm looking for my x-intercept, that's when y is 0. What is the x value going to be when y is 0?
4.
Beautiful. Point. And what is the y-intercept going to be when x is equal to 0?
6.
The y value is going to be 6. So I have this point. Excellent. Y'all are fantastic. Okay, so now I'm going to connect those two, and since it's or equal to, it's a solid line. And am I going to shade above to the right or below and to the left?
Below and to the left.
Beautiful. Okay, so if I try to identify all the intersections, it is going to be, well, let me do that in black. There's my feasible region. So I graphed all the constraints and I got my feasible region. Okay, so if I'm going through the steps, I did step 1. I graphed the constraints and I found the feasible region. Now I have to determine the vertices of the feasible region. So if I'm looking for the vertices of the feasible region, I know I see how many points. How many vertices do you see? I see one here, and I know that point.
4.
4.
Okay, so my first point was 0, 4. I have another vertex here, which was which was 0, 1.5. I have another vertex here, which is 3, 1.5. And then I have another vertex here, which is 2, 3. So I've identified the 4 vertices. So I have a table here that I like to always create where I state my vertices. So I have 4 vertices. Now, I know my objective function, it was given to me. So all I'm going to do is evaluate my objective function at each of these vertices. So if I were to substitute in each of these vertices, I'd get P equals 25 times 0 plus 30 times 4. So this is going to go to 0. So my value of my objective function P is what?
120.
Beautiful. Now I'm going to do the same thing at that next vertex. So 25 times 0 plus 30 times 1.5. Again, this goes to 0. 30 times 1.5 is going to give me an objective function of what?
45.
45. And then I'm going to keep going and I'm going to evaluate the objective function at the third point. Okay, a little bit more work, a little bit more arithmetic. So this is going to give me 75 plus 45. So the value of that objective function at that point is what?
120.
Beautiful. And then last but not least, I evaluate the objective function at the last vertex. And I'm going to get 50 plus 90, which is going to give me what value of the objective function?
140.
Beautiful. So now I've done the third step. The third step was to evaluate the objective function at each of the vertices of the feasible region. Now, I want to find the minimum and I want to find the maximum. So if I'm looking at the minimum, what is the minimum value? The minimum value of my objective function is 45. So I would say that the minimum is 45. And where does that occur? At the point 0, 1.5. So this was our minimum. Now, the next thing you're being asked is what is the maximum? So if I'm looking at the value of my objective function, my maximum value, is going to be 140 at the point 2, 3. Does that make sense how we did that? Yes?
Yes.
Okay, fantastic. So
That's
let's,
okay. Oh.
yeah,
Let's say that, like, if the maximum value was shared between 2 of the ordered pairs, would you put both of them?
you would. Yes, you'd say the maximum value is, let's say the 140 didn't even exist. You would say the maximum is 120 and it occurs at, and then you'd state both points. Yes, yes. Very good, very good. Excellent. Okay, let's do another example. Another example. Word problems, because I know you love them. A bookstore manager is purchasing new bookcases. The store needs 320 feet of shelf space, that we need that. Now, bookcase A provides 32 feet of shelf space and costs $200. Bookcase B provides 16 feet of shelf space and costs $125. So I'm seeing my variables. Now, because of space restrictions, the store has room for at most 8 of bookshelf A and 12 of bookshelf B. I see some constraints. The question is, how many of each bookcase do I want to purchase? So how much of each, if I want to minimize the cost? So I want to determine how many of each bookcase I'm going to buy to minimize the cost. So first, let's define some variables. Variable X, let's let X represent the number of bookcase A to buy. And again, I like to write the other things next to it. I know it provides 32 feet and it costs $200. I'm just trying to keep all my variables straight. That's not part of the defining of the variable, but I like to go ahead and write it next to it. Now, my second variable, Y, is going to be the number of bookcase B to buy. And what do I know about it? I know that it provides 16 feet of shelf space and costs $125. Now, my objective function is to minimize cost. Minimize cost. So if I want to minimize cost, my objective function is going to deal with how much these things cost. So I'll call it C for my objective function. You can call it whatever you want. My cost is a function of buying bookcase A and bookcase B. Now, I know bookcase A, well, does anybody think they can come up with the objective function? Anybody think they have a clue? About minimizing cost? No? $200 for every bookcase A I buy, plus $125 for every bookcase B I buy. So I want to minimize that cost. I want to minimize that C. Are there any questions on how I arrived at my objective function C? I'm going to assume no. Constraints. Let's write constraints. First constraint.
Has to be less than 8.
What has to be less than 8?
A.
Okay, and we define that as X, so I like it. So you're saying X has to be less than or equal to 8, right?
Yeah.
Okay, so that has to do with my space constraint. Anything else?
Y has to be less than or equal to 12.
Beautiful. That's another space constraint. What else? Can I have negative bookcases?
No.
No. So X and Y have to be greater than or equal to 0 as well, right? So those are actually, we would call those non-negativity constraints. And last but not least, there's something else, another constraint that I have. Do we have any idea?
Would it be the total cost or?
That's our objective function, but I like that you're thinking about that. So the only information we've been given has been about cost, but what else?
The feet.
The feet. So weren't we told that we need 320 feet of shelf space? At least we want to get at least 320 feet of shelf space. So I need to write another inequality constraint that represents, by adding the shelf space from each of these bookcases, we had 32 feet for every bookshelf A, plus 16 feet for every bookshelf B. Anybody finish that inequality?
Equals 320.
Equals?
Is
We want at least 320, right?
greater
So,
than or equal to.
yes, there you go. That's beautiful. That's beautiful. Now, if I wanted to, so this is our shelf space requirement, right? So now I'm going to start graphing these. Okay. Now I know X has to be in between 0 and 8, right? Let me not do it like that. Let me shade it. So from here and here, I know that I'm looking at solid lines at 0, shading this way, solid lines at 8, if I can see that little, shading this way, right? You see how I took these two pieces of information and I shaded this region here?
Yeah.
Okay. Now I'm going to do the same thing with Y. Y has to be greater than 0 and less than 12. Boundary lines are solid and I'm shading this region. So I'm already confined to that rectangular region. So last but not least, I want to go ahead and graph this. So it's, again, want to do intercepts, want to put it in slope intercept form? I don't care. However you want to do it. How do you want to do it? Anybody have a preference? Intercepts? Sure, since nobody said anything, we're doing intercepts. So I'm looking at this inequality here, and I'm looking for my x-intercept. What is the x value when y is 0?
20.
Okay. And then, I'm sorry,
10.
what's, sorry, 10, not 20, yeah. And, no, well, let me just rewrite that because that's hideous. And then what is my y-intercept when x is 0?
20.
Yes. Okay, so I'm going to plot those 2 points, 10, 0, 0, 20. And it's a solid boundary line, so I'm going to go ahead and graph a solid boundary line. And am I going to shade above and to the right or down and to the left?
Above.
You are absolutely correct. So if I'm trying to find my feasible region, it is going to be in here. Isn't that my only place that is graphed by all of them? So let's identify the vertices. I have 3 vertices. What are my vertices? Can anybody tell me what they are?
4,
8, 12,
4, 12, yes. What else?
8 and 12,
8 and 12, and last but not least,
8 and 4.
8 and 4. Now, if you can't easily tell what they are, you may have a system to find that, but you can do that. Now, let's look at the objective function. Our objective function was C, and let's evaluate the objective function at each of those vertices. So that means 20 times 4 plus 125 times 12. What is that going to give me? What is that objective function going to yield? You have calculators. Tell me what it is. Do each of these and tell me what they are. I'm just evaluating the objective function at each of these vertices. At the point 412, what is the objective function? Somebody do the arithmetic.
2,300.
Beautiful, thank you. We obtained that by doing 800 plus 1,500. Excellent. What about the next one? What is that going to give me? Next one. Anybody? I know the answer. Do you?
2,100.
3,100. Right. And the last one, at the last vertex, what is the value of the objective function?
2,100.
Yes. Now, remember, I'm being asked to minimize the cost. So which one of these represents the minimum cost? This one, right? This is the minimum. So how would I represent my answer? I would say this is a word problem. To minimize cost, the manager should buy 8 of bookcase A, right? 8 of bookcase A and 4 of bookcase B. And the cost would be $2,100. There you go. Now, in the last few minutes, let's just for kicks, let's just for fun, because we love to graph in Desmos, let's go ahead and graph this problem. Because why not? So I'm going to take each of those 5 constraints. I have x is less than or equal to 8. I had x had to be greater than or equal to 0. Now I could have put those together, right? And I'll put the y's together because why not? 0 is less than or equal to y is less than or equal to 12. So you see how I wrote an extended inequality? I could have done the same thing with the x's. Okay, and then last but not least, because this is where we are, I have 32x plus 16y is greater than or equal to 320. So here's my feasible region. There's a vertex. There's a vertex. There's a vertex. So you never know, you may have a project where you're going to have to do some more problems and you'd have to do all the steps we just did in this. Define your variables, identify the objective function, write the inequality constraints, graph the feasible region, identify the vertices, evaluate the objective function at the vertices, and answer the question. Got it? Any questions on linear programming?
Do we have homework?
You know that you do. You know that you do. And what's happening next week?
Test.
You have a test. So let's make sure that we're looking at Canvas and doing any and all preparations for that test. And if you don't have any other questions, you are welcome to go start preparing for that and doing the homework and getting ready for that test next week. We will be in the library next week, next Tuesday, for the test. So make sure that you know, you're preparing for that. Also, you know, if you join the math club, our first math club meeting is today after school in our Teams meeting. If there aren't any other questions, you are free to go. You have a few seconds left before the end of class.
By the way, is there a test review or?
Is there a test review? Can anybody answer that question?